Okay, so in this video we're going to talk about solving PDEs by the method of separation of variables. So let me first remind you of what we did in class the other day. We had certain requirements that have to be satisfied in order to actually use the method of separation of variables. So the first requirement was that the PDE, both the PDE and the boundary condition had to be linear. So basically, for an operator to be linear, if you apply L to a linear combination of U1 and U2, you should be able to say this is equal to a linear combination of L of U1 and L of U2. Secondly, the PDE and boundary condition both had to be homogeneous. So basically, this meant that the right-hand side had to be equal to 0. And you also had to have the spatial variable had to have finite boundaries. So you can't use separation of variables if you have infinite or semi-infinite spatial boundaries. The reason why we're interested in linear operators is because of this principle of superposition. So basically, if you have any two functions, u1 and u2, that satisfy a linear homogeneous equation, then any combination of these functions also has to satisfy the same equation. Okay, so let's look at the method of separation of variables. To do this, we're going to talk about a sample problem. So here we're going to consider the heat equation with perfect lateral insulation, no source term, and both ends immersed in a 0-degree bath. So if you just pause for a little bit, maybe think about writing down this mathematical model yourself like you did in the first couple of homework assignments, and think about what this problem would look like. So here, with the perfect lateral insulation, you do not have any terms like alpha u. No source terms mean you don't have a q. So basically, all you have is the general heat equation, u sub t equals ku sub xx. Both ends being immersed in a 0-degree bath means at the left-hand side, you have that u is specified to be 0 degrees. And at the right-hand side, your function u is also specified to be 0 degrees. And you always have some kind of initial condition where u of x0 is equal to some function of x. And we'll talk about these initial conditions a little bit later. Okay, so method of separation of variables. In this method, we basically assume that the solution has the form phi of x times g of t. So here, I want to point out that phi of x is strictly a function of x, and g of t is strictly a function of t. So now we're going to substitute this into our PDE, and what we're going to notice is something nice happens. So here our PDE is the heat equation. So in the left-hand side, we plug this in. We're going to have the partial with respect to t of our phi g. The right-hand side, we're going to have k times the second partial of phi times g. Okay, so notice here on this left-hand side, we're taking the partial with respect to t, but here phi is just a function of x. So phi is constant with respect to t. It's going to be able to come straight out in front. So what we're going to end up having on the left-hand side is phi of x times, now g is a function of only t, so this is a regular derivative, not a partial derivative. Similarly, on this right-hand side, g is a function of t, so again, we're going to be able to take that out. So we're going to have k g of t, and again, phi is only a function of x, so this is a regular derivative. Okay, so now we're going to separate the variables. So this is just the equation we had on the previous slide. We have phi dg dt is equal to k g of t, second derivative of phi with respect to x. So notice what we can do is we can take this g to the other side. We can take this phi to this side. So here we have 1 over kg dg dt is equal to 1 over phi, second partial of phi with respect to x squared. Second derivative, sorry. So notice that the left-hand side is a function of only t, and the right-hand side is a function of only x. The only way a function of just t can equal a function of just x if both are constant. So we're going to let the left-hand side and the right-hand side both equal a constant lambda, and we're actually going to have it equal a constant negative lambda. And here the negative is just for convenience. So lambda is known as to be the separation constant. So here we have a function of t equals a function of x. The only way that you can have this is if it's equal to the separation constant. So now we can actually separate this into two ODEs. So if we look on this side, we can look at this 1 over kg dg dt equals negative lambda, and then we could look at this right hand side. So this 1 over phi d squared phi dx squared is equal to negative lambda. So here is our first ODE, or we could actually write it as just dg dt is equal to minus lambda kg. Our second ODE we can write as the second derivative of phi is equal to negative lambda phi. So remember, we have our boundary conditions. So u of xt equals to our phi of x g of t has to satisfy the boundary. Our u of 0t is equal to 0, and our u of lt is equal to 0. So this is that homogeneous boundary condition. So what does this mean? So at the left-hand boundary, we have u of 0t is equal to 0, which means that phi of 0 g of t has to equal 0, or simply phi of 0 has to equal 0. Similarly, at the right-hand boundary, we have phi of L g of t has to equal 0, or simply phi of L is equal to 0. So there are boundary conditions for the spatial ODE that we have, but no additional conditions on the ODE for G. Okay, so now let's look at solving the time-dependent ODE. We have two ODEs. They're totally separate. We can solve them separately. So remember how to solve an ODE like this. You can split it up. You have dg dt. You can separate the g and the t. So we have dg over g is equal to lambda k dt. Now we just integrate both sides. So we integrate the left-hand side, we get natural log of g. Integrate the right-hand side, we get minus lambda kt plus c. Solving for g, we simply have g of t is equal to some constant times e to the minus lambda kt. Okay, solving a spatial ODE is slightly more involved. So this spatial ODE, remember, is the second derivative of phi with respect to x is equal to minus lambda phi. And we also had our boundary conditions, phi of 0 is equal to 0 and phi of L is equal to 0. So this is called a boundary value problem. So if you remember this from ODEs, there are some values of lambda for which there's a non-trivial solution. So by trivial solution, I basically mean b is equal to 0. So there's only certain values of lambda in which you don't just get the trivial solution. So let's consider three possibilities for lambda. So these are going to be called eigenvalues. And the solutions that correspond to these values of lambda are going to be called eigenfunctions. So the first case that we're going to consider is lambda is less than 0. We're going to consider lambda equals 0 and lambda is greater than 0. Okay, so first looking at case 1, lambda less than 0. So with this case, basically we have our ODE here. And to make things a little bit simpler, we're going to assume lambda is equal to negative s because we're assuming lambda is negative. So here we assume that s is positive. So just substituting in, we have d squared phi dx squared is equal to s phi. So remember this, the way that you solve an equation like this is you get the characteristic equation. So here our characteristic equation is just m squared is equal to s, or solving for m we get m is plus or minus the square root of s. So we have two distinct roots for our characteristic equation. So our general solution is given as c1 e to the square root of sx plus c2 e to the minus square root of sx. Normally this is not written this way. So normally instead of writing it this way, we actually write the general solution in terms of the hyperbolic cosine and hyperbolic sine. So just to remind you of what these are, so here's the hyperbolic cosine is just a combination of e to the ax and e to the minus ax. Hyperbolic sine is another combination with the minus sign in between. And these are the graphs. And so the graphs are actually going to give us a little bit of what we need in order to finish out finding our constants for our solution. So remember what we have. We have our solution phi of x is equal to some constant times the hyperbolic cosine plus c4 hyperbolic sine. Now we can plug in our boundary conditions. Remember, we have the phi of 0 and phi of L both have to equal 0. We're going to use these to solve for C3 and C4. So plugging in phi of 0, we have cosh of 0 is just 1. The sinh of 0 is 0. So we get C3 is equal to 0. So C3 is equal to 0 basically means that this part's gone. So now we plug in L into this boundary condition. So we have C4, sinh of square root of SL has to equal 0. So remember what we're looking for is what is C4. So remember the graph. So if you look kind of back up into what we had before, the graph here, the only time that the hyperbolic sine is equal to 0 is when x is equal to 0. So going back to what we had before, we have the C4 sinh of square root of SL is equal to 0. Sinh of x is equal to 0 only when x equals 0, which means that the sinh of square root of SL cannot equal 0. So the only way this is satisfied is the C4 is equal to 0. So basically that means that phi of x equal to this, the only way that phi of x equal to this satisfies our boundary conditions is if both C3 and C4 is equal to 0, which we conclude that lambda is negative 0, we only get the trivial solution, which means lambda can't be negative. We're only looking for non-trivial solutions. Okay, so in the case lambda equals 0, recall our ODE. So here, the case that lambda equals 0, we just have this part is equal to 0. So now we're going to get simply that phi of x has to equal C1x plus C2, which is something that we've seen over and over again when we've been looking at those equilibrium solutions. So now solving for C1 and C2, again we plug in our boundary conditions. Phi of 0, we simply get C2 has to equal 0. So now we have C2 is equal to 0, so plugging in L into this part, we just have C1L. The only way that this can be equal to 0 is if C1 is equal to 0. So again, we have that lambda equals 0, we only get the trivial solution, so lambda can't be equal to 0. Okay, so lambda greater than 0. For lambda greater than 0, again, we have our ODE. We can look at our characteristic equation. So the characteristic equation gives us just m squared is equal to negative lambda. So here, remember that m squared is equal to negative lambda. So remember, lambda here is positive, so this whole thing is definitely negative. So we can find our roots. We have two imaginary roots. Remember, the way that you write your solution when you have imaginary roots is our phi of x is a linear combination of our cosine and our sine. So we have our phi of x is equal to C1 cosine square root lambda x plus C2 sine square root of lambda x. So now again we're going to solve for C1 and C2 by plugging in our boundary conditions. Plugging in the left-hand boundary, we get C1 is equal to 0. Plugging in the right-hand boundary, we have C2 sine of square root of lambda L is equal to 0. So this looks like what we had for hyperbolic sine here when we had the lambda less than 0. But remember, here this is what a sine curve looks like. There are several times at which you can actually get sine equal to 0. So sine of x is equal to 0 whenever x is equal to n pi. So what this tells us for this part of our equation is that sine of this is equal to 0 whenever this part is some multiple of pi. Where here, remember, lambda is positive, so n has to be 1, 2, strictly positive. And n is any integer. So what this tells us is that this sine is equal to 0 whenever lambda is square root of lambda L is equal to n pi, or lambda has this form. So we have eigenvalues lambda n with this, and with those we have eigenfunctions where C2 can be anything, and sine of n pi x over L is our function. Okay, so now we put everything together. So we have our u of xt we said was v of x g of t. We solved for g of t. We solved for phi of x. So we get any non-trivial solutions whenever lambda has the special form. So the products of our heat equation have to have this v times this g, or simply if you combine the c and the c2 together, we can say that this is some constant. So notice here that the lambda as t goes to 0, this part goes to 0, so this whole thing goes to 0, and that u of x0, the initial condition, has this special form. So if we have some kind of initial value problem, so for example, suppose we wanted to solve this initial value problem, where here this looks just like what we've been solving, but now we've specified f of x. We know the general form for something of this form has this solution. So now if we just set b equal to 4, n equal to 3, then we get that this solution satisfies our PDE, satisfies our boundary conditions, and it also satisfies our initial condition. So suppose we have a different type of initial value. So now suppose we have something that looks more like this. So we know by the principle of superposition that we could have two solutions with the same form, the form that we found before, but instead our B1 and our B and our N are two different things. This still satisfies our solution. If one of these satisfies it, then both of these satisfy it. So now what we can do is we can choose our B1 to be 4, our N1 to be 3, B2 to be 7, and our N2 to be 8. And so now we have that this is a solution to our PDE. So what about initial values of a different form? So we're going to actually get to this, and we're going to look at that. We can actually have forms that don't look like this specialized form. And we're going to use what's called Fourier series to solve these type of problems. So that's for next time.